Calculus! AP Calculus. We are in that class, lesson 7-4, position. Today is January 9th, 1/9. Make sure you have the date, your name on the piece of paper. All right, today we're talking about position. So each of these lessons is a specific part of a free response question. Each unit is designed around one specific free response question. Today's lesson corresponds to the most points for this free response question, so make sure that we really understand what's going on in today's lesson. All right, so again, we're talking about Mr. Frog. I love Mr. Frog. Maybe to make it gender neutral, maybe I should switch it to Mrs. Frog every other lesson, but so far we're with Mr. Frog, and he's hopping down a road. He has his velocity. Our domain is between 0 and 5, and we have this equation, which does work out nicely. I've already tested it. It's the natural log of t squared minus 3t plus 3. I need to know when he's farthest to the left and the right, given that his position is, he starts at 8 when time is 0. By the way, do we bring our calculators today? I just forgot to ask that.
Oh, I think I left mine.
All right, Rochelle, go grab yours. All right, we have calculators. So these questions are kind of hard to answer. When is he farthest to the left and when is he farthest to the right? It really helps to look at a graph when we're looking at this function, because I don't know what natural log of this quadratic looks like. It's probably some quadratic in like transferred over a log function. In fact, this is what it looks like. You can see how it's kind of a quadratic, kind of like that natural logarithm where this goes farther and farther. It doesn't have any horizontal asymptote, but you can tell it is kind of like a logarithm. So how am I going to do this? Let's go ahead and graph this. We already know how to graph this from yesterday, right? Right. Okay, so let's go ahead and do that again. Let's open up Mr. Sandell's calculator. I have the ROM loaded correctly. All right, so again, we're going to go to y equals, and my function is hidden. There it is. So it's going to be natural logarithm of, it's going to be x squared minus 3x plus 3. And our window is going to be between 0 and 5. So 0, enter, 5, enter. And then how do I make sure that it's zoomed correctly? Zoom 0. There it is. Zoom 0. And you should get this graph, theoretically. And there it is. You're getting that graph. Give me a thumbs up if you're there. Yeah, we're all there. Okay, so we need to figure out when he's farthest to the right. And we've talked about this lesson on, it was before Christmas break, but in terms of how far you travel, that's always the area underneath the curve. So if I'm looking at the area underneath the curve, and we can actually add this to our notes, this area here, and you can do little bars here, this area right here represents positive area. You're traveling forward or traveling to the right, traveling up, some positive distance. So I'm going to say that area right there, that's positive. However, this area down here is negative. This area down here, that's negative. And then this giant area here, which is, you can tell it's like way bigger than either of those two, that giant area right there is definitely a giant positive. Each of those areas represents some distance that you're traveling, because the integral of velocity is position. So this integral represents position change. All right, so I want to figure out how much the position changes with each of these areas. So I have to somehow calculate each of those areas. We are no longer in the realm of, oh, you find a rectangle and a triangle and I found the area. Now we need to use and utilize this calculator to find the area. Here's how you do it. I'm going to do the steps on the calculator. You're going to follow with me, and then I'm going to come back to the notes and copy down what we did. So let's find the area of this first shape. So I go to second, trace, and I have my calculate menu, and I'm going to hit 7 because 7 corresponds to the integral. You can see that little integral symbol down there. You can actually scroll down and hit enter if you want, but the quicker way is just hitting 7. It's saying, okay, where's the left-hand side? Where's the right-hand side? The lower limit, the left-hand side, we can just hit 0. So type 0, then enter. That's the lower limit. The upper limit, we somehow need to figure out where that intersection is. I happen to know that it's 1 offhand just because I've done this problem before. But if you didn't know where that was, you would have to calculate where the 0 was first. Let me repeat that because I think that's confusing. We don't know where this intersects the x-axis exactly, but I'm telling you it's 1. But if you didn't know where it was, you could do second calculate and find the zeros using yesterday's lesson. So far, so good? All right, so I know that the upper limit is 1, so just type in 1 and hit enter. And your calculator will do that. And it will tell you that area is 0.554818112, and it rounded at 2.
555.
Yeah.
Is it rounded?
555. Whoa. I wonder if it's the difference between the emulated calculator and the non-emulated calculator.
Well, it's just a rounding difference, and that might be a setting.
Okay. That is interesting. Okay, let's just assume it's 0.555 then. I don't know why mine didn't give me that. Okay, so let's go ahead and label that on our graph. This area right here is 0.555. 0.555. And it's positive, so I left it positive. Let's go ahead and find that next area. So that's going to be between 1 and 2. So you know how to do that. So let's go back to our calculator, and you know the same steps. It's second trace to go to calculating the integral 7 between 1, enter, 2, enter. And it will go right there. And notice that it doesn't unshade the previous area, which is kind of annoying, so you don't know if you're doing it quite correct. But I do know this is correct. I got negative 0.186. Is that what you guys are getting? So that's going to be negative 0.186 for that negative area. And go ahead and do it for the next one. It's going to be from 2 to 5. Second, trace, 7, 2, enter, 5, enter. You'll get fast with this over time.
It's satisfying to see it.
It is, yeah. I got 4.371. This area here as 4.371. And by the way, all of AP Calculus rounds to 3 decimal places. You will never, I've never seen at least a problem that says round to 2 decimal places or round to 1 decimal place. It's either round to the nearest whole unit, which does happen, or in these cases, round to the nearest thousandth. So round to the nearest 3 decimal places. All right, so we have our notes labeled. We know how big each of these intervals is. Let's talk about this first interval. Let's come back up here to the number line. Where did Mr. Frog start?
0.
At time 0, but where was his position? Read the problem again. Where did his position start? Notice that 0 isn't even on our number line, so it's probably not 0. At x equals 8, yeah, so this is the start. We can label that too. Squeeze that in there. He starts at 8. Let's go ahead and put a little point at 8. That's where Mr. Frog starts. Now, after how many seconds? Where was this point right here?
1.
After 1 second, he is now 0.555 further to the right or to the left?
Right.
To the right. Okay, so after 1 second, he has now gone, well, not to 9, to 0.555. So right here to 8, I can kind of label this down here, I guess, 8.555. And that's in 1 second. Okay, what happens next? Well, in the next 1 second, he goes back 0.186. And I'm not even going to do the math, but you can kind of see what's going to happen. He's going to go backwards 0.86, and then he's going to go forwards a giant amount, 4.371, so he's going to jump forward all the way over here somewhere. I don't know where it is exactly. We'll have to do the math. But he's jumping forward, backwards, and forwards in different amount of seconds. Are we okay with what is happening in this story? Let's talk about how we actually solve this before we go on to our new notes. What do we do to find these areas underneath the curve? Well, the first thing that we did was we did second, trace, and again, these notes are for you for a month or 2 months down the road when you might have forgotten how to find the area underneath the curve. Second trace, 7, and that will bring up the calculate menu. We are now calculating, by hitting 7, we are calculating the integral. Then you needed to do the lower limit. So we're doing the lower limit. And we did that by hitting the buttons 0, because 0 is the lower end of the limit. And then we hit enter. Next, we found the upper limit. Got some lag there. Upper limit. And we did that by hitting 1, because our upper limit of x was 1, and then we hit enter. This was at time 2, this was at time 5, that was at time 0. Okay, perfect. So how do we actually find end position? And it's exactly what we did in this story. make sure that you know where you're starting. So my formula looks like this. It's going to be, and this is, I'm doing it in red because it's super important, it's start. Not 0, but wherever you started. And then you add, so this is not a t, it's plus. Start plus whatever integral you're talking about, plus the integral. That integral is going to represent the change in position. So, I should do this, I apologize. Can you erase the integral? We'll do the integral down below. We'll do the kind of the English definition on top, and we'll do the symbolic definition on the bottom. So this is going to be the change in position, plus delta position, plus the change in position, and that will be what we're looking for. We're looking for the end position, so I'm just going to say that's going to equal to the end. And here's the symbolic definition for at least what we did in our problem, right? So our problem, we started at 8. We're going to add the integral. Let's just talk about getting to the end position of, let's just pretend we wanted to end at time equals 1. What's the integral going to be for the bounds? Between what and what? 0 and 1. 0 and 1 of our function. Our function happened to be this function right here. You can write natural log of all this stuff, but we're lazy. I'm just going to write vt, because vt represents the velocity function of natural log of all that. So I'm going to say 0 of 1 of vt dt. And that will be equal to, and we actually wrote it down up here, it's 8.555. So that's going to be 8.555. All right. So what we're eventually going to do is we're going to be making a table to check all the values of t that are important. But the question now is, what values of t are important to check? There's always 3 of them. Every single time, there's always 3 of them. But you might be smart enough to eliminate a few of these, and I can talk about that in the future, but I don't think it's a topic for today. So the first thing that you always need to check is your start. You have to check that start position. There are some cases where that might actually be the answer. You might start, or you might be the farthest to the left wherever you start. You need to check every single CV. So check every CV. What's the definition of a CV again?
Critical value.
Critical value, yeah. What's the definition of that?
V of t equals 0.
Yeah, v of t, or velocity equals to 0.
They don't have to be sign changes.
That's a good question. Do they have to be sign changes? So your question is, if you have a graph like this, where you come down and just touch it, does it need to be a sign change? I would say,
Or if the graph like starts at x equals 0. I mean, it's kind of.
you're right. It doesn't need to be a sign change. No, it's just wherever it's 0. Sign change might be a better way of, it might be a faster way of doing it though, because
Yeah.
that's going to be positive, that's going to be positive. It's impossible for that to be the farthest to the right because you're already going more right.
Yeah.
So let's change our definition. And I'm actually changing John's notes by doing this, but this is a smarter way of doing it, and you're right. So instead of saying check every CV, let's check every, what's the definition of a sign change? Sign change is the definition of,
When I change the
The
sign.
height of the. Yeah. Anyway.
we'll just say height change, I guess. Or v equals 0 with sign change. So if we're on the graph of v, that's really the graph of the derivative, because our normal function is position, so v is the derivative. So where, in this, we should know this, f prime sign change, what is the definition of? F prime is equal to 0 is a CV, but f prime sign change is a,
It's not inflection.
no, it starts with an e.
Oh, relative extreme.
There it is.
Well,
It's extrema, I guess, but We'll say relative extrema. That's the better way of saying it. Every v equals 0 with a sign change. So wherever it crosses the x-axis, and maybe that's an even better way of saying it. Wherever you cross the x-axis, that's the point that you need to check for a t value. And there's going to be probably more than one. Sometimes there's only one. Usually there's going to be 2 or 3. And finally, you need to check your n value. So you might have 3 things to check. You might have 5 things to check. But these are all the values of t that you need to check. So let's go ahead and set up our table. And you'll notice that the homework also has a giant table. Our table. Every single time that you have a free response that give you a giant white area, go ahead and start by making a table. Whenever they're saying, when is it farthest this way, you set up a table, you say t, you're going to write our definition for finding the end position, start plus change in position is equal to end. So, start plus change in position is equal to the end. Okay, what are the values of t that we need to check for this problem? Look at our graph.
0, 1, 2, and 5.
Yep, I agree. 0, 1, 2, and 5. 0, 1, 2, and 5. Put those in our table. Make sure that you look at your graph on your calculator or on the notes and make sure that that makes sense. 0, 1, 2, and 5. Where do we get those values from? Got it? Got it, Era?
Yeah.
Okay. Then where do we start with each of these? What position do we start?
8.
8. Each of these is going to be 8. 8, 8, 8, and 8. Each of these is going to be adding to plus, 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 plus the change in position. Okay, this one is kind of dumb because we haven't changed position at time equals 0 yet, so just leave this one blank. Technically, if you wanted to be pedantic about it, from 0 to 0 of velocity with respect to t, but the integral from something to the same position is just 0. It's nothing. Okay, the next integral is going to be from where to where? 0 to 1 of velocity, vt, dt. Next one is going to be from where to where? Someone aside from Rochelle? Careful. So we're always starting back at time equals 0. You're always going to start at 0 here. Always going to start at 0 here. But what's the upper limit going to be? 2. Yep. And Ben, upper limit of the last one is going to be?
5.
5. And then all of these are vt, dt, vt, dt. All right. Now we have to do some calculator work. We already calculated what those areas are, so now we actually have to, well, I guess we have to do a little bit more work. What we could have done is instead of entering in each of these individual areas, we could have done the graphical integral from 0 to 2, and then it would have added 0.555 with negative 0.186 for us. But we're just going to do that right now on our calculators. So what is this end position at time equals 0? 8 plus 0 is? 8, good. 8 plus, I know the integral from 0 to 1 is 0.555, so it's going to be? 8.555. Notice that these table values refer to what's happening on this number line right now. Now I'm going to subtract 0.186 from 8.555. What do I get? And you're just doing this on your calculators. We see it? Do we get 8.369? All right, here we are. 8.369. And finally, we have to add our 4.371. So on our calculators, you can do second answer. So second answer, and it's that little negative symbol.
What if you just do plus?
Or you could just do plus in it.
And it'll automatically answer.
That's a faster way. Never mind. Just do plus. 4.371. 12.740. 12.740. All right. We have our answer. We just need to identify it. 1 second, Daisy. Our questions were, when is he farthest to the left? Look at your table. When was that? Which of these is farthest to the left?
2.
Time equals 0. So our answer here is time equals 0, and then the position is 8. When is he farthest to the right? What's our answer? At what time is he farthest to the right? T equals 5. T equals 5. Position is the highest. It's a relative extrema. It happens to be the extrema of all of it. 12.740. 12.740. And that concludes the notes. Any questions before we write our summaries? All right, thank you.